Okay, so time to get started. Sorry for this slightly late start. So last time we were talking about the very, very beginning of a new collection of big theorems. And like I say, they all have, so there's some really exciting things about them, and their applications, really interesting stuff. And they all have something to do with the fundamental theorem calculus. Right? So the very first thing we did, well, the very last thing we did last time, but the first thing we did along these lines is to go back and talk about the fundamental theorem of calculus again. And it's a bit of a weird point of view, you might say, on the fundamental theorem of calculus. Certainly there are easier ways to get to the fundamental theorem of calculus as a result. But let's think of it as follows. It's a way of computing change, f of b minus f of a. The exact opposite of how people mostly think of it, but let's think of it that way. Notice that change is an accumulating quantity, right? Now again, this seems like a trivial observation. The total amount that f changes is the sum of the amounts that f changes on each little piece along the way. Well, yeah, that's how change works. It isn't that obvious, you might say. But it's worth observing, it's very valuable to observe here, that this is a feature that this quantity that we're interested in computing has that many other quantities of interest don't have, right? So we used the example last time of centroids. Not an accumulating quantity. The centroid of an interval is not the same as the sum of the centroids of the pieces that you chop it up into. It's wildly false, right? Okay, so this has this feature of being an accumulating quantity. Make that observation first. Thus getting us down to here. And then we observe that if you just multiply and divide by delta x, perfectly free, right? No problem there. Then, lo and behold, you end up with something that is an integral, pretty much, right? I mean, yeah, there's this issue of what happens when you take the limit inside of the soon-to-be integrand, and that's an issue of formality that we're not going to focus on in Math 212. Trust me, it works out to be fine in this case. There you go. We were computing change, and we viewed it by viewing it as an accumulating quantity and pulling a little algebraic trickery. We ended up with writing it as an integral. Okay. All right. So then I ended with the observation that you can view this as making a statement about a new kind of a density that we've never really thought about as a density before. Whoa. Sorry, that jumped up fast. I didn't mean to do that. Apologies to the YouTube crowd. I'm sure that's a big, someone's got their earbuds in and it's just bam. Okay. All right. So here's a related thing that we've talked about. So mass is an integral from a to b of density dx, right? And so this is what we call mass density. Right? This is what we call mass density because it's the density. It's the integrand in the resulting integral that we get in a computation of mass. So therefore we call this mass density. Well, here's the thing. In a computation of change, this is the resulting density. This is the integrand in the resulting integral. So we call it change density. So, and like I say, it's a new point of view. Most people don't think of the derivative this way. I think this is surprisingly useful to think of the derivative not as a slope, not as a rate, not as a factor, but as a density. Brand new point of view. By the way, if you're a little uncomfortable with that, let me draw another picture over here. Here's a picture of how we normally think of derivatives let's think of derivative as a slope of a graph. So, at this point, for example, we draw the usual little triangle, and we talk about the rise over the run. That's the way to think about slope, right? Well, but you can see it right here. That's the amount of change that has happened over this little piece of width, which of course is a size. So this is a quantity per unit size. I mean, that's how you think of density, right? Again, we haven't applied it in this way, in this context, but stuff per unit size is how we think of densities. I mean, that's the generalized notion of a density. So the only thing that makes this, the only sort of extra detail that, quantity per unit size, the only extra detail you need to really interpret that meaningfully as a density is that stuff is an accumulating quantity, and change is. Right? So this is just the accumulation of a different kind of a stuff. It's just a stuff that's not physical. And we're not accustomed to thinking of it as stuff. But change is stuff. I want you to think of change almost like it's a physical thing. Of course, it's not physical. But think of it as if it's a kind of physical thing because it behaves that way algebraically. Okay. Alrighty. So now I'm going to rip off this argument that we made here. Again, the purpose of going back and talking about the fundamental theorem of calculus, because this is going to serve as a template for understanding other theorems. And here we go. Let's suppose now, instead of moving from A to B on the x-axis, suppose I'm going from A to B through space along a curve. Right? And let's, again, just kind of ripping off, just, hoping to, let's copy from what happened last time and fingers crossed, kind of hope something cool happens. Maybe we'll get lucky and develop a theorem, right? So, very often math happens this way. Let's look at change, right? We can imagine some function defined on R2 or R3, right? There's nothing about this picture that prevents it from being an R3. Maybe there's some function on R3, real valued function. Think of it as temperature if you like, whatever. And I could ask the question, how much does this function f change between the point A and the point B as I move along the curve? Well, first observation, change accumulates. Right? It's just like it accumulates as you move along an interval on the x-axis or the t-axis. Likewise, it accumulates as you move along a curve. Here's a different metaphor. You can think of this curve, this blue curve that I have there, as being representing a road on a map. Right? So this is a two-dimensional picture, and this represents the road on a map, and maybe f represents altitude. Right? So if you want to compute the total change in altitude between the point A and the point B, well, the total change in altitude is the sum of the changes in altitude that you experience each step along the way. Again, well, of course, right? Change accumulates. There's nothing deep about this. Okay. All right, so we write that down. Just like we did last time, we're going to throw a limit out front because we can and because it makes it look more like an integral, which is kind of what we're kind of hoping to be able to negotiate this into, right? Because we like theorems. So now what did we do at this stage in the last step? Well, we rewrote that like that. So specifically, we both multiplied and divide by delta x. Okay, said differently, we figured out how to view delta f as something times delta x. I figured out how to get a delta x over there, which is what I really needed to be able to interpret this as a integral. Right? So, well, here's the analogous thing here. Delta f, if I want this to look like an integral, and the easiest way to do that is observe, and this is just a callback to chapter 13, chain rule if you like, but delta f is the gradient dot delta x. Right? Totally chapter 13. This represents the change in input position. This represents the change in output value of the function, and the relationship between input change and output change for a real valued function defined on R2 or R3 is dot product with the gradient. Okay. All right. So again, we find ourselves with an expression that looks familiar. That looks just like a what I like to call a vector line integral. Right? That's exactly what that is. A vector line integral. Specifically, it's a vector line integral of this special vector field. Well, I'll do it like this. This special vector field, that remember we saw this back in 15.1. This the gradient of a real valued function is a vector field, despite the fact that we never thought of it that way back in chapter 13. And so, hey, look, lo and behold, we have a new theorem, right? I mean, copying works sometimes. It's a long and proud tradition in math to take ideas that work and say, hey, let's apply this idea over here in this kind of semi-related. Let's just, again, cheating off of what worked before, and hey, hopefully this will work out. And it has. Right? So here's our new theorem. It's called the fundamental theorem of line integrals because it looks just like the fundamental theorem of calculus, except for line integrals. So the name is pretty unsurprising, right? And just like with the fundamental theorem of calculus, right? Fundamental theorem of calculus you think of as, even though we sort of derived it in that way, we started thinking of it as, hey, let's compute change. You know, the reality, of course, is that we tend to use the result as a way of computing integrals, right? So let me just get this back here because I'd like that. Yeah, there we go. So likewise, here we're going to use this very often as a way of computing line integrals. Everybody on board? Yep.
What are A and B like in the original thing?
Yeah, so it's just we imagine some scenario in which we have some starting point A, some ending point B, and some curve that goes from one to the other. Yeah. Right. Okay. All right. Now, before we move along, we did have this idea of density that was conjured, right? I mean, the integrand here in our brand new theorem ended up being density. Yeah, a weird point of view, but how about that? So before we go on to see some applications, can we do something kind of like that with our new theorem here? Right, the fundamental theorem of line integrals. Can I interpret, I guess, gradient as being a kind of a density? And sadly, not quite. It doesn't work perfectly here. Let me point out the analogy. Here's sort of the analogous calculation on a curve relating to mass and thus motivating the use of the term density. Mass accumulates, right? We've done this kind of thing before on curves. Problem is, ds and dx are not the same. Right? ds is a length, a size, right? dx is a vector. It's a displacement. It's a significantly different thing, right? So what I have to really do in order to make this kind of fit the comparison that I would like to force in here, I have to rewrite f of b minus f of a equals integral over the curve, and then I'm going to use the book's notation, gradient f dot t ds. So remember, this is an alternative way of writing a line integral, a vector line integral. Right? Same thing, just a different way of writing it. And now you see the analogy really does hold. So here we have, there's a ds, there's a ds. These really are analogous things. I mean, in the same way that mass accumulates with a corresponding notion of mass density, well, likewise, change accumulates with this as its corresponding notion of change density. So it's not, sadly, it's not the gradient. The gradient itself is not the density. It's gradient dot t. That's the density. So a little bit of not exactly sort of analogous. So the way I want you all to think about this, and I'm going to just kind of plant a quick thought here. We're going to come back and go into more detail with what happened here a little bit later on when we have a more immediate use, a more immediate application of a deeper interpretation here, is to just point out that, well, so what that means is that the gradient by itself doesn't tell you the density, but it does tell you a lot about density. I mean, think about what gradient is. Gradient has a magnitude. It's a vector, right? It's got a magnitude that's telling you change per unit distance traveled in that direction. It's telling you change per unit size. Just, asterisk with the assumption that you're going in the ideal direction, and if you're not going in the ideal direction, if you're going off at a different angle, then you got to take the dot product to get the cosine in there to account for what the actual change is, right? So yes, there is that asterisk. But a different way of thinking of that is that the gradient is telling you two things. It's telling you what is the change per unit distance. What is the rate of change per unit distance? Right? And in addition to that, it's also telling you in what direction that change per unit distance is happening. So it's not just telling you change density. It is also telling you the direction that change is happening. And therefore, we often refer to directions as orientations. And so I like to call the gradient an oriented change density. Right? It's got the starting change density. That's really what's fundamentally happening with the function itself. And it has, furthermore, an additional tool that tells you how to adapt that information to what's relevant to your personal interests. Namely, I'm going that direction, right, instead of that direction. Okay. All right. So, so the gradient is an oriented density. Fine. Well, let's leave that there for a little while. We'll come back to it next week or the following. I don't remember exactly when. Okay. All right. So, we're going to use the fundamental theorem of line integrals very analogously to how we use the fundamental theorem of calculus. First of all, in order to use this to compute an integral, two things. Your integrand has to be a derivative of something. Now, let me go back to the fundamental theorem of calculus. Here it is. Notice that in order to use this theorem, your integrand, you can see it right here. The integrand has to be a derivative of something. There's that prime. This theorem does not say, hey, here's a formula for computing the integral of anything you should so choose. It says right there, integral of a derivative of something. And only derivatives of something. Okay, so your integrand's got to actually be a derivative. And then furthermore, of course, in order to use the theorem, you have to actually be able to find that antiderivative, right? So go back over to here. If you're going to use this theorem to compute such a thing, you need to know what the antiderivative little f is, because that's the thing that you have to plug into in this formula. Okay. All right. So the same is true for the fundamental theorem of line integrals. The integrand has to actually be a gradient of something. Again, you can see it right here in the theorem. If you want to compute a line integral, you can see it right here. It says, blaringly, this computes integrals of gradient fields. Right? This will not just compute integrals of whatever random vector field you feel like. It's got to actually be a gradient. And secondly, the thing whose gradient is the vector field, what I like to call the anti-gradient. Yeah? What I like to call the anti-gradient, you need to be able to know what that is, because that's what you plug into in the function. So the terminology anti-gradient I motivate because it's totally analogous to the term antiderivative, right? I think it's highly plausible. Okay, so good news, bad news. This is almost always true, right? In fact, every continuous function, you may remember this from Calc 1, a long time ago, but every continuous function is a derivative of something. So part 1 is just really never an issue for the fundamental theorem of calculus. And of course, you all know all about part 2. You got to be able to find the antiderivative. So that's why a sizable fraction of a Calc 1 and 2 courses go into computing antiderivatives. All right. The bad news. This right here, the vector field in question being a gradient, not always true. The analogy just flat breaks down, right? Almost every function, let's say, be precise. Every continuous function is a derivative. Not every continuous vector field is a gradient. So the analogy's just not perfect. And then furthermore, you've got to be able to find the anti-gradient if there is one, and that's a matter of technique, and we'll talk about that in a few minutes. Okay. All right. So let's get our hands dirty and do one. Suppose we're asked to compute a line integral. Here you go. Now, y'all have techniques for this, right? You can parameterize the curve, and you can plug in and do the pullback, and again, deep breath, plug and chug, and you can do it that way, right? as y'all recall, sometimes kind of tedious. Okay, so we're going to try to outsmart that here. By the way, notice that the curve is already parameterized. How convenient, right? It's almost like it's suggesting that you should do the pullback and do the parameterization, because look, here's the parameterization. Go ahead, right? And now let's see. Now here's the vector field. So you got a vector field, you got a parameterization, and how do you compute this integral? So rather than parameterize, and by the way, let's try to handicap this this problem. How hard would it be to do this, pulling back through the parameterization? Well, don't forget, this is x, that's y, and that's your z, right? So whatever x's, y's, and z's show up in here, there's gonna be some kind of algebraic ugliness that gets inserted wherever there's an x, y, and a z. And then, of course, dx has the derivatives of these things in them. So this thing here is going to be sort of, algebraically unpleasant. This is going to be algebraically quite tedious if you use the pullback. Okay, so let's outsmart that. I make this observation. I'm going to pull this out of thin air. Talk more about where it came from in a few minutes, but this vector field is a gradient. How about that? Now you got to check and make sure that's correct, right? Think about how do you take the gradient of this function x plus yz and compute the appropriate partials. And well, sure enough, it's that f. Okay, so the question we've been asked, I want to compute the line integral of some vector field, but it's not just any old random vector field. This is the special kind of vector field, namely a gradient, that our theorem addresses, right? Line integral of a gradient. Okay, so all I need to do is find the anti-gradient and plug in. Oh, right, good news. We already found the anti-gradient, right? The thing whose gradient is our vector field. That's anti-gradient. We stubbed our toe on it. We just, pulled it out of thin air in this particular case, but hey, there it is. And so we're off to the races at this point. The theorem tells us if you want to compute a line integral of a gradient, take the endpoints, plug into your anti-gradient, and compute. And it's just plugging in. Right? There's no sort of calculus to do. There's no dot product to worry about. You just plug in. And so let's a couple of details. So the starting point of this curve is where x equals 0. So you plug in x equals 0 into that curve, and that gives you your starting point. That's your A, if you will. Then plug in x equals 1 into here. That gives you your ending point, your B, as it were. Right? And plug these into your function, right? So this is your f. So these 2 points plug into your f, get these two values, and there's your answer. Very convenient, very slick. Everybody see what happened there? Powerful result. We just avoided a bunch of calculations, which, by the way, would have worked out if you had done the pullback. Yeah, it would. I mean, it just would have been this great big nasty thing, and it would have been inconvenient and tedious and lots of pencil lead. But it would have worked out that way. But I like doing it in a way that requires much less work. All right, so let me take a pause here for a moment before we go on. Anybody have any questions about how this went down? Okay. Okay, so how did I do this? I just pulled this out of thin air, right? The anti-gradient. How did I know x plus yz is the thing that was going to work? How did I know that anything was going to work? By the way, right? We've made this observation. Well, I've made this assertion that not every vector field actually is a gradient of something. So how did I know that there was any anti-gradient at all? to be found, much less how did I find it. Okay, so we're going to answer both of those questions. We'll start off with the mechanics. How do you actually find the anti-gradient? Well, keep in mind, here's what we have. There's a vector field, F. Whatever the vector field F is, it's got coordinates. Remember, we have this convention. We're going to use P, Q, and R to represent the coordinates. Fine. And I would like for that to equal to the gradient of something. Okay, well, reminder, that's what a gradient is. Right. So, if you would like your function to be if you would like your vector field to be a gradient, note that what that means is that the three coordinates of your vector field, those have to be the x, y, and z partials, respectively, of this mystery function that you're looking out for. Right, we're trying to find that anti-gradient, that function whose gradient is my vector field. So its x, y, and z partials have to be P, Q, and R. And if you take those three statements and just say them backwards, right? So, for example, if P has to be the x partial of F, well, then analogously, F has to be the x anti-partial of P. Right, and likewise on down. So you get these equations here. Okay, well, except a little minor detail. Now, we have to, realize that when you take an antiderivative, there's always this plus c thing, right? The idea of the plus c is that, well, technically, if I were to take the x partial here, anything that's constant, when I take the x partial, that goes away, and this would still give me the, p equals partial of f with respect to x that I'm looking for. So any constant over here is fine, except that now it's no longer technically quite a constant. It's anything whose partial with respect to x is 0. That's what's really going on here. This just needs to be something that will disappear when you take an x partial. And all that means is it can't have any x's in it. Right? So I'm going to call them constant functions, which sounds sort of contradictory, but you kind of get the idea, right? So these are constant functions of the other variables. So C1 of y comma z is what I'm going to call this function here. And you take an x partial and it goes away. All right, so likewise here, this can be anything that when you take a y partial will disappear, etc. Okay. All right, so roughly speaking, then, here's what your process is. Your vector field has three components. Those components take the corresponding antipartials. Take the x antipartial of the first one, the y antipartial of the second one, the z antipartial of the third one. Don't forget to add in your, who knows what these constant functions might be, and then just try to find. If we're looking for this function f, try to find a single function that will satisfy all three of these equations. All three of these equations have to work. And you may or may not be able to find a function, a single function, little f, that satisfies all three of these equations. But if you do, then you're good. Okay, so example. Let's find the anti-gradient of this function right here. Well, I'm going to follow the procedure. We're going to take the first coordinate, and we're going to do an x partial. And then we're going to take the second coordinate. We're going to do a y partial, and then we're going to take the third coordinate and do a z partial. Right? And now this is just a little bit of antiderivatives. Those are pretty easy antiderivatives. Just don't forget they're antipartials, right? So you're taking antiderivatives with respect to the appropriate indicated variable there. Don't forget to add in your constant functions, right? And now begins the game. So I'm looking for some function f that could equal to all three of these things. And, well, is it possible? Is it... first reaction might be to say no, because look, that's different from that. These things are different, therefore there's no one thing that can equal to two different things. That just, lose, right? Until you remember, oh, wait a minute, there is this business over here. Maybe that's YZ. right? At which point all of these things really are equal. If I were to just say, okay, let's let these be 0, and then look, all three of these things are in fact equal. They're all xyz plus yz. So that's my antigradient. So you see the game element of it, right? You have to have the clever insight to realize, what do those functions on the right, what do the constant functions need to be so that it all fits? All right. All right, now, I claim that this will not always work. In fact, we already knew this. We didn't think about this at the time, but when we talked about, y'all remember I made these kind of mysterious assertions that, interesting things happen when you compose these, back in 15.1. We've got these operators that were introduced without context, just had a thin air, and then I made this assertion that interesting things happen when you stick them together like this. Well, here's one of them. Given a vector field, how do I know if there's an antigradient? Well, if Green's operator gives me 0, then there is. This is that lifetime theorem, right? So if you have a gradient, Green's operator is 0, and furthermore, if Green's operator is 0, then it's a gradient. So effectively, whether or not Green's operator is 0 tells you, by way of this theorem, and again, just for the sake of repetition, we're assuming that all these functions are perfectly nice and there's no irregularity issues, and that's very important, and we don't want to get bogged down in that right now. So assuming everything is nice and no issues. If Green's operator is 0, that arbitrates the question of whether there is a gradient or not. We didn't think of it that way at the time, but anyway, that's how we're going to use it here. And then likewise, in 3 dimensions, so this is in R2, right? So in 3 dimensions, if you have a vector field given and you would like to know, is it or is it not a gradient of something, or said differently, does it or does it not have an antigradient? The answer is, take the curl and see if you get 0. And by the way, of course, it remains, I've given you no reason to believe why it is that these diagrams do what I claim that they do. And we'll kind of motivate that a little bit later on in the course. We just don't quite have the tools just yet. But nevertheless, this, again, is a tool that we can use at the moment to at least answer the question, yeah.
So is Green's operator the 2D version of...
Yeah, you can kind of think about it that way, and there is some ways in which I kind of prefer not to think of it that way, but in a lot of ways, yeah, absolutely, yeah. It's certainly playing the analogous role here. So, if you're in 3 dimensions, take the curl and see if you get 0. In 2 dimensions, take Green's operator and see if you get 0. So, yeah, you could make this very reasonable case that Green's operator is kind of a sort of a 2-dimensional curl. Yep. All right. Okay. So let's use that here. Here's a vector field. Does it have an antigradient? Let me say that differently. If I were to play the game, if I were to write out the x antipartial, the x antipartial of this, the y antipartial of that, the z antipartial of that, and then start playing the game of what can I be? Can I choose these constants in such a way that it'll make these all, can you win that game or not? Right? But how about without actually going to the trouble of playing the game? And so here's the answer. This is a 3-dimensional vector field, so we take the curl. If there's going to be an antigradient, we need the curl to be 0. Here's our formula for curl. Again, out of nowhere. We'll justify that somewhat later on. At least we'll give a context for it. And we start computing, and let's see, the y partial of r, there's r, take its y partial. The z partial of q, well, there's q, take its z partial, subtract, and that first component of curl is this, which, by the way, is not 0, so I don't even have to compute the rest of this. Right? My question is arbitrated by whether or not this curl is flat 0. I need all the coordinates to be 0. I need that to be 0 as a vector. Right? And even though I've only computed one coordinate, I can already tell it's not 0 as a vector because the first coordinate's not 0. So this right here tells me the curl is not 0, and therefore there is no antigradient. Don't try to find it. It's not there. Everybody on board? It's a wild goose chase, as it were. Okay. Okay. All right. Yeah, okay. All right, so here's the beginnings of what I think is a really nice tool, nice way to organize a lot of these ideas in your mind. And we've sort of just scratched the surface, by the way, of Chapter 15. We've seen one new theorem. We've seen one theorem kind of like the fundamental theorem of calculus. And there's going to be quite a few more, several more, right? So there's going to be a tremendous amount of ideas thrown at you in the next couple of weeks here. And keeping those ideas kind of sorted and organized in your mind is challenging. So the following diagram is a start of an organizational system, I'll call it, that I think is really useful. And there's other advantages as well. So here we go. There are certain kinds of objects that we're going to talk about when we talk about the fundamental theorem of calculus. By the way, this is a diagram that relates to the fundamental theorem of calculus. You can see right down here, fundamental theorem of calculus. And so here are the objects that are in question. We're going to be looking at certain kinds of what I like to call evaluations. Evaluations take different form, but they're mostly integrals. Okay. The idea is you give me a function, you give me some collection of points. What does it mean to take a function and these collection of points, and what's the output value that I associate to? You give me a function and some geometry, and what do you get out of that? Right? What I'm going to call column 1 are objects involved in that question that are what I'm going to call ultimately one-dimensional. So one-dimensional, meaning that if you look at the set of points, here we have a one-dimensional interval. Right? That's so a collection of points on the x-axis, A to B, that kind of a thing. That's a one-dimensional thing. This is what it means to evaluate a function on an interval in this context. This is a way that you can take a function and an interval and out of those two things produce a number. That number being the value of this integral. The integrand is a function in this case. Okay, all right. Column 0. Well, zero-dimensional sets of points are just points, right? So an interval is one-dimensional. Zero-dimensional means just a point. And this is a kind of a silly observation, but if you give me a function and a point, then I can plug that point into that function and then evaluate, right? So this is what I'm going to claim is the natural kind of evaluation in this context. By the way, all of this diagram, nothing that's on here is actually rigorous. This is just an organizational system that I want you all to kind of think in terms of. And again, you'll see over the development that we'll do in the next couple of weeks how I think this is a really useful organizational tool. Okay, so what does the fundamental theorem of calculus say? Well, if you give me a function, and if you take a derivative of it, so we have this operation of derivative. You take a derivative of one function, you get another function. Okay. If you give me an interval, I can talk about the boundary. Right? So notice the boundary of an interval, A to B, the boundary consists of, well, just those 2 points, A and B. Okay. So if you give me a function and then you give me an interval, then notice the act of taking the derivative of the function, the act of taking the boundary of the interval, if you plug these boundary points into that function, right? If you take this derivative function and over the given interval do an integral, you get the same thing. Okay, so the idea, and again, we're not proving anything here. This is just a way to sort the ideas out in your mind. I claim that there's going to be this big deluge of ideas that you need to sort of be able to structurally organize in your mind, and this is, I think, a great way to do it. The pattern that we're starting is, if you take a derivative of a function, if you take a boundary of an interval, then this evaluation, plug in the boundary points into the original function. This evaluation, take an integral of the derivative over the original interval, give you the same thing. So that's the pattern I want you to notice, and I make the observation that the fundamental theorem of line integrals follows the same pattern. Now don't look at this stuff over here just yet. We're not ready for that yet. We'll get there. Okay, I'll just leave the rest of that. Same deal. If we think of gradient as what you can do to a function to give you a vector field, noticing that vector fields over one-dimensional curves are evaluated with line integrals. Notice that taking the gradient, here I'll do it down here, the gradient of a function, taking the boundary of a curve, that evaluation gives you that evaluation. Same pattern. This isn't a deep observation in this context. I mean, you already noticed that the theorems looked a lot alike, and so therefore, well, let's just write it and lay out the objects in the obvious way, and of course the pattern's going to hold, right? But much more is going to happen where that is going to be much less obvious, and yet the pattern will still hold. All right, so this is just kind of set up. By the way, likewise in 3 dimensions. Again, we're not ready to look at some of this stuff yet. Let's don't look at any of this yet. We'll get to that later. But gradient, boundary, evaluate, get the same thing. Okay. All right. More on that as we go along. Okay, so new topic. I want to talk about path independence. This is the way I'm going to start by stating it is this is a property that a vector field might have that at your first glance might even sound implausible. Like, how could a vector field possibly have this property? Here's the idea. Notice the vector field that has this property. I didn't draw it. The picture gets too messed up. But just try to imagine, what could the vector field possibly be that would have the following feature given any 2 points A and B that are fixed. I would like for this vector field to have the feature that if I were to compute its line integral along that curve, and if I were to compute its line integral along that curve, I would like to always get the same answer. And by the way, not just those 2 curves, any curve from A to B, however wacky, I want to always give me the same value. Now, you might think to yourself, okay, well, that's a lot of curves, by the way. Right? How many different curves are there to get from A to B? It's uncountably infinite. Right? So you might think, okay, look, I can rig it up, though. I mean, I can be sort of, strategic, and I can make the vector field such that, along this curve, it does whatever this line integral says it's supposed to. But then what do you do along that curve? Right? If you set up the vector field so that along the green curve it does what it's supposed to do, mightn't you be kind of messing it up for along the red curve? The very process of making it good on one might make it bad along the other. It seems like a real trick shot that a single vector field could have the feature that all of these infinitely many line integrals all give you the same value always for any given two fixed points A and B. Seems like I say, seems like a perhaps unrealistic request. Okay, until you realize that we actually already know a whole bunch of vector fields that do this. So here's, let me remind you of our fundamental theorem of line integrals, and that is that the integral along a curve of a gradient is f of b minus f of a right? And here's the thing then. As long as I pick, so once I've picked the A and the B, right? Well, A and the B are now fixed. Take any function you like. I don't even care. Well, it's got to be continuous and differential. Well, anyways, let's not worry about the regularity. Any nice function, right? The right-hand side will be fixed. Once you decide what little f is, that right-hand side, f of b minus f of a, it is what it is. And it does not matter what curve you pick to go from a to b, f of b minus f of a is always the same, right? Once you picked a function. And so then, well, along that curve, what is the value of that line integral? Well, it's f of b minus f of a. Okay? What is the value along this curve? Well, it's f of b minus f of a, right? What's the value along this curve here? Well, we round about, I suppose, but the value of that integral is f of b minus f of a, right? So clever observation because of the fact that we pick a function f, nail down what your function is, then the gradient field has this amazing feature that no matter what curve you pick from A to B, the line integral will always be the same. Yeah?
How would all those curves have the same gradient?
Well, keep in mind, curves don't have gradients. Oh, sorry, I hit the button again with my elbow. HDMI, there we go. Curves don't have gradients. The function has a gradient. The function is what dictates what the vector field is. The curves come after the fact, right? Pick a function that gives you your gradient field. The vector field is set, and now pick whatever curves you want. Right? Does that make sense? Yeah. Okay. So here's. Oh yeah, go ahead.
But don't they all have to be the gradient of the same function?
Yep. Well, so there's only one vector field here, right? So we pick a function little f, and we're once that little f is picked, then that dictates what its gradient is. So that single vector field, gradient f, is the one vector field that we're talking about. And that one vector field, you take all these different curves here, that curve or that curve or that curve, moving through that same gradient vector field. Their line integrals will all be computed by this same formula and therefore get the same answer. Yeah.
So how do you know, with the curves, are the curves?
The whole point to this is that the curves could be anything, right? So we're looking for a vector field that has a certain property. The certain property is that for all curves, the same thing always happens. That make sense? So here's an analogy. Here's a way to think about it. Again, let's think about the curves through R2, and let's think about roads and altitude. Right? Here's a not very shocking fact. If you have a starting point A and an ending point B, it doesn't really matter how you drive from A to B. The change in your altitude is always the same. Right? So the change in your altitude, though, if you think about it, the change in your altitude is a line integral. The way you compute a change is with line integral of the gradient. Right? So roughly this observation that we're making here is kind of analogous to when we finally get old enough in our lives to realize that our grandfathers were lying to us when they said they had to walk, uphill both ways to school. No, you can't. That's not you can't. No, granddad. The total altitude gain. It come on, it's fixed. Okay. All right. So this is called path independence. A vector field that has this property. So the gradient here is the vector field that has this property of path independence, and all gradients are path independent. And again, that's demonstrated by the fundamental theorem of line integrals, like we did there. Okay, and that's a good stopping point. See y'all later. Have a great weekend.